The brain's cleansing system has only been recently discovered, may be a key component to healthy cognition. In this video and the next, we look at how the glymphatic system works, and more importantly, what we can do to make it work even better. Sleep is a great mystery. A trait shared across animal species, sleep must be of vital importance to survive natural selection pressures to eliminate such a vulnerable state. Indeed, cringe-worthy experiments have shown that keeping animals awake long enough can be fatal within 11 to 32 days. It turns out sleep is of the brain, by the brain, and for the brain. One function of sleep that has been elucidated in recent years is the clearance of toxic waste byproducts through a newly discovered drainage system in the brain. With the invention of the encephalogram, EEG, to measure brainwave activity, the scientific world was quickly disabused of the notion that sleep was a time of rest for the brain. During certain stages of sleep, there was brain-wide activity going on, but what was the brain actively doing? More than 2,000 years ago, Aristotle proposed that sleep helps the body clean the blood. Well, today, we know sleep may help the body clean the brain. Until 2012, we thought that the brain was singular among organs for recycling nearly all of its own waste. It had to, since it was separated from the rest of the body by the blood-brain barrier. But the barrier that keeps toxins out of the brain presumably keeps toxins in. Then, in 2012, a brain-wide fluid transport network was discovered, termed the glymphatic system. By microscopically tracking dye injected in the brains of mice, scientists discovered fluid-filled tunnels surrounding blood vessels in the brain. The pressure wave of arterial pulses with every heartbeat milks the fluid along before eventually draining into the cerebrospinal fluid surrounding the brain. What does this have to do with sleep? The whole system is only really active when sleeping. During wakefulness, these tunnels are clamped down, reducing glymphatic flow by 90%. The thought is the fluid shifts might interfere with targeted neurotransmitter chemical communication in the awake state, so the biological need for sleep may reflect the need for the brain to enter into a state to filter out potentially neurotoxic waste products like beta-amyloid, which is implicated in Alzheimer's disease. Perhaps this could help explain why those who routinely get fewer than 7 hours of sleep a night are at increased risk of developing cognitive disorders, such as dementia. Randomizing individuals to have their sleep disrupted by a series of beeps administered through headphones in a sleep lab increases amyloid levels, whereas improving sleep by treating sleep apnea patients with CPAP, for example, improves slow-wave activity, deep sleep, and appears to lower amyloid levels. PET scans show even a single all-nighter can cause a significant increase in accumulation of beta-amyloid in critical brain areas. The problem is that glymphatic brain filtration appears to decline with aging. Old mice only have 10 to 20% the glymphatic function of young mice. This could be due to a number of factors. As we age, we experience less of the deep, slow-wave sleep, the type of sleep during which brain waste clearance appears to be the most active. Further contributing to the stagnancy, our arteries tend to stiffen as we age, reducing the pulsations that drive the glymphatic pump. That also offers one potential explanation as to why hypertension is tied to dementia. The thickening of artery walls with high blood pressure also has a stiffening effect. How can we counter this age-related glymphatic decline and keep our brains cleaner? We'll explore just that question next.